recording as well so that we can share it with others. So can you guys hear me? Can someone let me know if you can hear me? Great, thank you. Cool. Let me start sharing my screen. Okay, so good afternoon, everyone. My name is Mahdi Kazimi, and I'll be covering, including this session, 3 of the workshops, this session and 2 later ones. And the plan for these workshops is basically to go through some of the contents that is hopefully something that could benefit everyone, because the thing is that this course is a project-based course, and I understand that you guys are dealing with different projects. Some of you are doing NLP tasks, some of you are doing computer vision, some of you might have other types of data sets like tabular data or anything, so other possible data sets. So it's a bit hard to cover pretty much everything, but I'll try to, I mean, the plan is we'll try to hopefully cover the most important ones, that is, as I mentioned, common problems or might help benefit everyone. But because it's kind of impossible to cover everything, every aspect of every sort of project, we might also keep the presentations a bit limited, so that we have at least maybe 10-15 minutes time at the end. If you have a specific to your project questions that I can help with, I'm happy to answer them. So that with that kind of introduction, let's start with the session. Today's session is about data and pre-processing, which is kind of the first step in every machine learning project that you start. So the contents, quickly, we talk about data inspection visualization, which is again the most of the time should be, it's the recommended very first step, unless you somehow already have gathered that kind of information from other, like if it is a public data set, there are papers on it, you probably can skip this one, but most of the times in real life, in practice, it's better not. And we see how to do some of the common visualizations with Matplotlib, which is a library in Python. And we see some of the data pre-processing steps that most of the machine learning algorithms, again, kind of irrespective of your task, need to be able to deal with. And a tool that is recommended in Python, again, you don't have to. The other thing is that you might be using different tools, different packages. Some of you might be using MATLAB, some of you might be using Python, but of course, our recommendation is Python, and the reason is that, like these days, pretty much everywhere, whether in industry or in academia, if you want to go both ways, most of the times Python is kind of something that is a requirement. And most of the packages in whether in classical machine learning or these days in deep learning are written based on Python. So that's recommended, but that doesn't mean that you need to stick to that. You can do whatever you like and whatever you're comfortable with, but that's the recommendation, and that's the reason for recommendation. And finally, splitting the data. So this session, as I mentioned, is about like all the steps that you should be taking or you should be considering as the first steps in your project to see the data, get familiar with the data, build your training testing set, if you already don't have them as a public data set. So as I mentioned, the first step is to inspect, get familiar, visualize your data. Why does it matter? I think if it's not very clear, the motivations are, first, you need to explore your data. Again, as I mentioned, here the assumption is that you are getting prepared for your future careers, whether it's in industry, whether it's in academia. In academia is a bit different. Most of the times you have data sets that are curated, training tests or training test split, everything is done. They're normally clean, like ImageNet, for example. You don't probably need to worry too much about these things, although sometimes they might help you further. But if you go to an industry, most of the times you don't even, there is a high probability you don't even have a data set. So you need to create your own data set, then you need to inspect it, visualize it to find out what potential issues exist in the data set, or if it is collected previously, but it has not been used for machine learning. It's very important to understand it and see what you have. So it gives you, by inspecting and visualizing it, you understand potential issues, you get the input-output distribution, and based on them, then you can decide what sort of machine learning algorithm is the best to go with. And if that's not a problem, that part, then the other motivation that you will definitely need to consider, and visualization plays an important role, is when you need to communicate, right? Most of the times, again, whether it's in the beginning of the project or at the end of the project, you need to be able to present your data, say, this is the data that we have. You need to somehow visualize it so that people can understand it quickly by having a quick look. So when you inspect or visualize your data set, there are a few things that it's recommended to look out for. Sometimes it depends on the type of data that you're dealing with. For example, whether you're dealing with images, text, time series, tabular data. So that's the first step, to understand what is the data that you're talking about. The next step is probably to see how many variables you have. For example, if it's images, you need to know the size of the input, the output size, so that you can design, for example, your neural networks if you're dealing with neural networks. Or if it is other time series text, you need to know, for example, in text, what is your vocabulary size. In time series, you need to know, for example, what is the frequency of the data that is collected, how many steps, for example, if you're doing, let's say, stock prediction, how many steps in the future you want to predict, and all those kind of things. So it's very important to see what variables you have. Again, something that I didn't probably mention is, what is the input, what is the output? Most of the times, some people come to you with a task and say, this is what I want to predict. And this is the data that I have. You need to then decide what variables are important, what variables you can probably ignore. And then after that, you need to understand what are the range of the values. So are you dealing with ranges in thousands? Are you dealing with ranges between 0 and 1? Most of the machine learning algorithms are very sensitive to the range of values. So, and we're going to see how to standardize them, normalize them. So it's very important to not to really skip this step, unless, as I mentioned, it's a public data set that there has been lots of papers on. It has been clean, pre-processed, everyone knows, and these are common sort of kind of knowledge in that community. If that's not the case, which is not the case most of the times in real world, you need to do these steps to make sure. For example, another thing is that there is a high chance that sometimes you have missing values in your data, right? For example, let's say the data is information that is collected about different people, their education, sometimes some of the fields, for example, let's say age of a person in a specific samples might be missing. Then you need to have a strategies how to deal with those. Otherwise, the results that you get are not going to be very reliable. So as I mentioned at the end, the main problem is that in real world, most of the times you cannot assume that you have an image net, that everything is known. It's clean, pre-processed, ready to use. So the other thing that when you deal with these data sets is that most of the times you don't have only 2 dimensions. You don't have only 2 variables to be able to visualize, or 3. So then you need to have more visual channels. You need to be a bit more creative and use other sorts of communication, other sorts of visual channels. These are known by visual channels, to be able to visualize higher dimension data in 2D in a way that in a glance, someone who is looking at your presentation, for example, right away they would understand, okay, this is the distribution of the data, these are the different variables that we have and how they are related. So the visual channels, you can see, you can use these different shapes, you can use different colors, you can use texture patterns, and you can also use these things that are known as color maps. And we are going to see in Matplotlib how they are going to be very useful. So the good thing about these color maps is you can use them to show ranges again in a glance. So let's say you are trying to visualize a heat map of the distribution of your data in different values. And by using a color map, you can show right away that, for example, what parts of your data, the parts that they look blue, for example, they are but they have very low values. The parts that are red, for example, have very high values. So these are very useful tools to communicate. And a good example is probably this one. Without caring too much really about the contents of this graph in terms of the variable names, which might be out of the scope of this class, like displacement, fuel efficiency. I think it's talking about an engine. But the message is that you have 5 variables here, right? And you have only 2 axes. How do you want to show them? Well, you can use two of the axes for the most important variables that you have. That's the fuel efficiency of this engine, displacement. But what about the 3 other variables? So you can use different shapes, for example, for cylinders. You can use size of the items, the visualization for the weight, and the color map, for example, going from very yellow or light colors to very dark green colors, whatever this color is, to show the horsepower. And you can see in a quick glance, even if none of us probably are familiar with this concept of whatever it is, engine fuel efficiency, but you can quickly see, for example, when the displacement is low, fuel efficiency is higher, and those kind of things. And most of the times, again, in that area, probably you're dealing with 4-cylinder engines. So it makes it very easy to understand the data for both yourself, if you're starting a project, to see what you're dealing with, to come up with ideas, to get a sense of what is a good performance and what are the outputs that you expect from the model. And at the end of your project, to visualize it, to communicate it with someone else. Especially this should be, or it's recommended to be, a good part of your project presentation, where you, if the data is not known, which you need to assume that is not known, you need to somehow send the message what type of data you're dealing with. So there are, of course, many different visualization libraries packages that you can use. But again, in Python, that is recommended. The most popular one probably is Matplotlib, although there are some other libraries like Pandas that has some plotting functions, for example, for tabular data to see the distribution of the data, or I think based on Pandas, there are some libraries that you can use for remote sensing and building maps, those kind of things. Again, some of these might be very specific to the type of data on your project, but Matplotlib is kind of a library that includes, that could be a good solution for many of the projects and covers most of the things that you're going to need in your machine learning class, not just this project. So based on that, we're going to get familiar with some of the functionalities that exist in Matplotlib. So in installation, I have put 2 links here for how to install a package manager. We have different package managers, but it's really out of the scope of the data pre-processing topic, which is the topic of this session. But if you already don't have a package manager in Python, then there are two kind of popular package managers, pip and conda. You can find out how you install them on these links below, and how to install the Matplotlib library. In pip is the command is just pip install Matplotlib. In conda is conda install. So those are the things that you can easily find on these links and other resources. So I don't think installation should be an issue. In terms of importing, just a quick takeaway message here is most of you might already be familiar with this, but there are some conventions that make your code easier to read and easier to follow, and for yourself makes life easier, right? Instead of, for example, importing matplotlib.pyplot, importing all the libraries, you can just give it a name as plt in Python. And that's very conventional name, as is, for example, NumPy. If you're not familiar, is another package that gives a lot of good mathematical functionalities, dealing with arrays. And it's a convention that people give it a name as NP. So it's good if you follow these conventions, makes it easier for both yourself to follow and others if they're reading your code. A quick note or a trick in Matplotlib if you're using it with Jupyter Notebook. So if you don't know what the Jupyter Notebook is, again, Jupyter Notebook is basically a notebook in Python that you can both write text and write code. The good functionality that it gives you is that every part of every section, like this in Jupyter Notebook is called a cell. And the good thing is that you can run every cell independently, and then so you can write a few lines of code and run that code and see if that works, and then like basically generate another cell and run it. So it gives you a good functionality when you are prototyping projects. It's normally easier than like coding in a normal text file or something, or even using the um, software such as VS Code or PyCharm. It's easier to code on a notebook, and it might also be easier to present it because, as I mentioned, you can quickly check, debug by running and seeing if it works, and it keeps all the variables in the memory. The reason that I told this was, if you're not familiar, again, there's links that how to install Jupyter, but that's kind of outside the scope. The reason that I mentioned is that if you're using Jupyter Notebook, it's good to note that Matplotlib works with it. And in order to work properly, you need to use this modulo Matplotlib inline, for example, if you want to make sure that your plots can be visualized in every cell. So another kind of recommendation when you're using Matplotlib is that every time you plot something or you visualize something, it's better to generate a figure object. So the figure object in Matplotlib is the base object that deals with every kind of plot, whether you create it explicitly or not, then this figure object is going to be created in the background. But it's recommended to basically create this figure object. So you have, for example, if you use this plt.figure, then the good thing is that you can, for example, pass in the size of the figures. And if you want to save that figure as an image, if you want to get the object access to the object itself, you can easily access it. Whereas if you don't define it and as we are going to see, jump directly to plotting something, then some of these functionalities might be missing. And in terms of code readability is also more important. The other thing is that if you don't generate figures, you can't really, every time you add an access, every time you add a plot, it's going to be a new figure is going to be generated in the background. Whereas if you want to, for example, on the right-hand side here, want to show 4 plots in the same figure, you can use this plt.subplots, and it gives you both the figure and axis. And what is on axis? Every kind of, you can see that these have, for example, here we have a 2D axis, we have rows and columns. Every axis is one of these, every single one of these plots. And that axis gives you a list of those that you can individually plot different things in every one of those. So it's recommended, if you don't, even if you don't need subplot, even if you don't need multiple plots, it's recommended to use the figure object so that you can use that figure later on, and you can add more access to it. So we are going to see some of the plotting functions that Matplotlib provides. Probably the first one, not probably, the first one that we are going to talk about is where you need to visualize data that you have y versus x kind of data, right? For example, if you have a sinusoidal wave that you want to visualize it, you can use Matplotlib plt.plot. And there are a few different arguments. The full list of arguments you can see at the following link, but the most important arguments is, of course, x and y. So the first value, if you only pass a single argument to it, it will assume that's the y, because it can figure out the x range based on the number of samples that exist in that y array or list that you have provided. But if you want to have a specific range of a specific number of samples in x-axis in specific ranges, you can provide them. So x and y need to have the same size. You can also use this numpy line space to say, for example, my x-axis, I want it to be between -4 and 4, and I want to have 100 samples. And based on those, you can see, for example, in the third plot here, during the first row, you can see the ranges between -4 and 4, although it's not visualized. We're going to see in xticks is another function, for example, that you can set what are the specific values on each axis that you want to show. But it's certainly between -4 and 4. It's just that 3 of them are shown here. The other important thing is that you can set the markers. So if you want it to be as a line, or if you want it to be as a dotted line, you can use this dotted marker. Or if you want it to be like a scatter plot as points, you can use all or a combination. So this is another kind of argument that you can pass on to say what sort of lines you want to use. And you can also say the colors. So C is where you can pass the colors. Again, you can see the full range of colors, but R means red, for example, B means blue, and so on. So you can pass these arguments to specifically say the shape, the color, and the type of line that you can use. The other important function in Matplotlib is basically where you have discrete points data that you want to show again in 2D in X versus Y. If you don't want to use plot, it's easier to use a scatter. It's again similar to plot X and Y, but we can see a few more functionalities. For example, now if you want to assign a specific title to your to any of these axes, you can use the set title function, or if you want to pass like a color map that we talked about before, any of these color maps, you can assign to the values, and then you can also pass the S argument is the size. You can pass on the size and so on. C again is the color. So here we are seeing that the color, we are giving it a value as a difference between the ranges. The edge color is another one of those arguments that says the edge of those. For example, if you're talking about circles here, the edge we want the edge to be black, so we can pass the edge color on as K. Another sort of the next probably good function that is very useful is to histogram. So most of the times, let's say if you are dealing with a classification, you want to show the distribution of your classes. So for example, in class 1, I have 10 samples. In class 2, I have 2 samples. It's very important because, again, in that example, if you know the distribution of your classes, if they are not evenly distributed, they're uniformly distributed, then you know right away in your data inspection stage that you're going to have a problem, because normally it's hard to train something that generalizes to all the classes where you don't have enough samples in one class, for example. Or you would also see the distribution of your input values. You see how many of those samples have value of between 30 to 40, or how many of them have a value between 0 to 30. So for that, you can use this histogram function. And the important thing here is that you need to either leave the binning, the number of bins of the distribution that you want to show, to the Matplotlib itself by saying auto, or you want to specifically say how many bins you want. Most of the times, you know in advance that you, for example, you have 5 classes, so you want 5 bins. You want to show the distribution in 5 bins. And what you pass as the input is the data itself. So you don't need to count the data. It performs the counting and it shows the histogram. Bar chart, again, another one of those that whether horizontally or vertically, you can use bar or bar H. The xticks that I mentioned here, again, usage of the function is similar to before, but xticks, you can basically here assign to every single value on your x-axis. You want to assign what that axis means, and you can use xticks, and you can input the number of those x-axis. For example, if you have 100, you can use range of 100. And then you pass the list of names. For example, this movie array, let's just assume that contains all these names. And now you're passing it as the y variable, and the rotation also is another argument. You can use it to basically say what each single variable on x-axis means. 2D images, there's this useful function in Matplotlib, imshow. You can either use it to show matrices, or you can show images. It doesn't really matter, because like images are also, depending on how you load them, of course, if they are loaded in a matrix shape, it can be visualized using imshow, or if it is just a single, let's say, single channel input matrix, you can also show it, and you can use the color maps again to show the 2D kind of distribution of things. usage is similar, but the difference here, we have another important argument, which is the min and max. So you want to set specifically what is the value of the minimum value that you want to show, so that the minimum value is assigned to the minimum value in your color map, and similarly for the maximum values. Yes, hopefully, again, these are a few functions in Matplotlib that gets you familiar and you can use in most of the tasks. There are, of course, a lot of further reading that you can do. There's a lot of good tutorials on Matplotlib itself if you want to go into more details, but this should provide like a general view of what Matplotlib is and what functionalities, important functionalities there are. So the next step, let's assume that you are past the visualization stage. You have seen your data, you have a good sense of your data now. It's at this step, again, assuming that this is not done, this is not a publicly available pre-processed data set. You want to check your data to see if it is ready to feed into any machine learning algorithm, or you need to do more. It's normally not, I mean, it's a rule of thumb, right? They say garbage in, garbage out. If your data is not ready to be fed into machine learning algorithms, if you use the state-of-the-art algorithm, you cannot really expect too much. So it's always a good thing to check if you need to do, and most of the times the standardization, at least that we're going to see, is a necessity. So even before that, you need to make sure your data is in numerical values. So if you're dealing with text, you need to convert that into numerical values, because you cannot put words in their own string shape. You cannot put them into machine learning algorithms. And need to have, it's what is missing here is need to have certain distributions. Sometimes you need to, so most of, again, it depends to some extent on your algorithm, whether you're doing deep learning, classical, SVM, what sort of machine learning algorithm. But most of the time the assumption is, or at least the benefit is to have, it's more advantageous to have a Gaussian distributed data as input, at the very least, to make sure that all of the data have a similar distribution. If you don't want to assume any specific distribution, that could be fine. At least you need to make sure that all your variables have a similar kind of distribution, or a similar range. So a good example to see the importance of it is, let's assume k nearest neighbors. And if you have forgotten or you haven't worked with k nearest neighbors, basically the idea is that, as the name suggests, you take a value of k, and your machine learning algorithm, basically, in order to assign a label to every variable that you input to it, it compares it with the k nearest neighbors. If k is 5, it compares it to the 5 nearest neighbors and says, okay, the label for this newly seen sample is the label of those, or the majority of both of those 5. Which means, in order to be able to compare, you need to have a distance metric, this as something to measure distance between different variables. And then there, basically, this range of values is very important. So on the left-hand side, let's just assume we have 2 variables, and one is in the range of, let's say, 7,000 to 12,000 or 13,000. The other one is way smaller values, between -1, 2 to 6, 7. Left without a scaling, right with a scaling. And if we run k nearest neighbor on this, what would happen is the decision boundaries in red and blue is going to be like this on the left hand side, in the sense that you are basically assigning all the samples in this vertical kind of bar to red, and everything else out of these 2 bars to blue. And you can easily see that this is not a good decision boundary, right? This is not a good way of training a classifier. And why this happened is because of this range, right? If here we are using, for example, Euclidean distance, if you move in range of x-axis very little, it's going to jump in terms of in range of thousands, right? Whereas if you move a lot in y-axis, let's go all the way from top to bottom, it's not comparable. The distance difference is not comparable to the x-axis range. And that's why this x-axis will dominate your decision boundary. Whereas if you do the scaling on the right-hand side, you see this is a more proper boundary. This is going to generalize. It's going to give you much better results. So that's why it really matters to first check your range of values that you're dealing with. Second, have a solution for it. And that solution most of the times means, at the very least, some sort of a scaling normalization. And for labels, this is a kind of separate from the example that I showed, but for labels, if you're again dealing with text, you need to somehow turn it into numerical values in a way that you don't cause problems, and we're going to see that. So scikit-learn for these kind of things, no matter what task you're dealing with, no matter your task you're dealing with, is not a good term probably, because if you're dealing with deep learning, you have, for example, in PyTorch and TensorFlow, you have your own pre-processing functions. But let's say out of deep learning, if you're using classical machine learning, if you're dealing with text, if you're dealing with tabular data, scikit-learn is probably one of the best packages to do this sort of scaling or standardization, normalization. There are many different, not many, a few different functions in scikit-learn that you can use to standardize your data. Again, it depends on your task. It depends on your data. It depends on your machine learning algorithm that you're going to use. But most of the times, a standardization is kind of the best idea and the requirement. And the reason is, as we just saw in that example, if you do not standardize your data, for example, the original data, let's say here on the left figure, it might have different axes, might have different ranges. And if you don't do it, something that happened with KNN might happen even with neural networks and many other algorithms. A standardization, what it does, it basically tries to make the distribution of your data Gaussian, independent on every single variable, which means that you're going to have less and less influence from the outliers or from large value axes or variables. You don't let them to dominate your decision. Because that's not a good thing most of the times. The way it calculates it, you make the data zero mean and unit variance by dividing the mean and by subtracting the mean and dividing it by the standard deviation. And you can see this data, for example, after standard scalar. This is called, in scikit-learn, it's called a standard scalar, the function that you can use. After standard scalar, you can see that the range of values are more reasonable. They are more reasonably distributed around the same or similar values. The other kind of normalization that you can use is, there is one here missing, min-max scalar. What min-max scalar does, it basically make sure that every variable has a range between 0 and 1. That might be a good thing if you know that you don't have a lot of outliers to dominate your decision. For example, let's say you have hundreds of samples in the range between 0 to 10, and then you have one single sample that has a value of 100, or even both 1,000. What happens if you do min-max scaling? You are basically considering the max of your data as 1,000, whereas you only have a single sample, which might be an incorrect sample. It might be a problem in your data set or in your measurement, whatever. That's an outlier, and you don't want to be too sensitive to that. That's the only problem with min-max scalar. Robust scalar is even more robust to these outliers, and the way that it works is instead of getting those statistics, mean and variance on the whole data, it divides the data between different quantiles and calculates them based on your quantile. So you can say whether you want it to be 25% quantile, 50% quantile. That's a hyperparameter or argument that you can choose. But it basically ignores more and more less and less common samples. It tries to ignore the outliers even more. Normalization is something that is commonly used in some NLP tasks, such as the task that you need to classify a document, let's say, and there's metrics. Again, without going into too much details, that might not be useful for everyone. Sometimes you need to classify a text, a piece of text, a document. You have like this metric of TF-IDF, and TF-IDF, you basically, the good thing that normalization does is that every single value is going to have a unit a unit norm. And then it's ready to calculate using a simple dot product, you can get the cosine distance and those kind of things. Most popular, most useful, probably most common is only a standard scalar, but depending on your task, you might need to do others. In scikit-learn, so the first few lines, it's about loading a model, loading a data set. The reason I put that there is because it's important that you don't want to extract your mean and variance. For example, if you're doing a scale, a standardization, you don't want to extract them based on your test data. So it's very important that you normalize your data. If you want to be 100% fair, there's no cheating. Because whatever is in test set, you don't really want to see, right? You don't want to assume anything about it. If you want to make sure that your model, the performance that you report is very fair. You want to make sure that your model performs well on that test set without really looking at it by checking the training set. So it's very important to fit your scalar on the X-train. So the function that calculates those metrics that are needed. Here, for example, if it is a standard scalar, you need to instantiate that class, and then you call the fit function on your training set, and it calculates mean and variance, and then you can use transform to transform any data. Now, you could use the same fitted values to transform your test set. That's fine because it's not going to calculate, but this fit is important to not to be called on the test set. So for all of those kind of scaling and standardization that are introduced, they will have this fit function. You need to instantiate the class, call the fit function, and transfer to transform your data. Moving a bit away from your input pre-processing or feature standardization, normalization. What if you're dealing with categorical data? So let's say you have, again, this is an example data set. You can use pandas to load it. But the idea is that you have a list of names. Of course, again, you cannot feed your names as a strings to your machine learning model. You need to assign a numerical value. How you do that is there are a few different ways. You can assign a specific values to them. But one thing that you need to be aware of, that it's not always a good thing, most of the time it's not even a good thing, is that when you, for example, say Manhattan is 2, Queens is 3, Brooklyn is 1, when you're assigning values to variables like this, because these are numbers have certain characteristics. Their range, their value is important to your model, whatever you learn, because your model doesn't see Manhattan, right? It only sees 2. So you're kind of implying, let's say Queens is the most important value because it has the highest value. What if your model learns to only look at the high values and ignore the small values? So the idea is that by assigning this kind of numbers to your variables, if that kind of order doesn't exist, if the higher the better or the lower the better, if these kind of orders and meanings of values don't exist in your data, which shouldn't exist, for example, if you're talking about city names or suburb names, whatever they are, then you shouldn't do that. A better way is to use one-hot encoding. And basically, one-hot encoding is that you will have a vector of the size of all the possible values that you have here. For example, if you're dealing with 4 or 5 different distinct values, you will have a vector of size 4. And then that vector will have a 1 where that value is assigned, for example, to Manhattan. Let's say Manhattan is assigned to number 2. So in your vector, number 2 will have a 1, the rest will have 0. This is called one-hot encoding. The good thing is you're not assuming any sort of order or any sort of, you're not assigning any single value to any of these. It's very useful, for example, if you're doing classification as the output, it could be used as the input as well. Then you can basically say that there's no order in the output, there's no importance. It's just we want to classify the input to one of these. In scikit-learn, again, you can do it in one line here, or you can use this the same way that we use the standard scalar. You instantiate that encoder and you fit it on your data. Here, because there's no kind of parameters that are extracted, or there is no values that are extracted from the trained data, it doesn't really matter if you call it on the whole data or not. It's just a transformation. So a few notes that or another topic basically is that what if you have missing values? So it's again very likely when you are given a CSV file, let's say, or a text kind of file, or many other different sort of file, that you have some missing values. There is some rows in your data set that don't have a specific variable. So how you want to deal with those is basically there are a few different strategies that might be dependent on your task, but the most general one is sometimes you just want to discard a certain value, a certain variable, and you want to say, okay, that variable, I know this is an expert knowledge, this is an expert knowledge. We know from the previous results or whatever that this variable is not important. Okay, we lose that. But sometimes that means that you lose some important information. If that's the case, you want to use other kind of techniques that are called imputation, which means that you impute that value that is missing using other information. So you can, for example, use the mean value of the whole data set. Again, this depends, these measures or strategies are dependent on your task. They might not be good for every task. Some of them might only work for some of the tasks. Or you might want to, another idea that is quite common is that you train a model to specifically predict that value, and then you do regress that value. Or you can use a combination of different strategies. So it's again important after visualization, pre-processing, you need to make sure that you know if there is existing values that need to be filled that are not, that don't exist. There are values, there are samples in your data set that have non-existing values. I think this is kind of the final topic before we can have a few minutes of Q&As on your projects. Best practice, again, not very dependent on the machine learning algorithm. In all of the algorithms, you want to have a split of the data set. You want to make sure that you put some of your data set aside as a test set so that you never touch it during training or validation, and you just test your results, your hypothesis on that, and basically report the results that you think are good. Basically, the distribution of these tests or the size of these tests could vary. It depends on the size of data set that you have. Normally, training set, people normally keep between, let's say, 70 to 80% for training, and then 10 to 20% for the validation, and the rest for the test set. There's also a good technique known cross-validation that you can use when you have very small amount of data to basically randomly split your training and validation so that your model sees all of the data and the reported results are a bit more reliable. I'll get to your questions in a second. So I just finish in scikit-learn. Again, if you have loaded your data, you can use scikit-learn, assuming that you are not doing deep learning. In deep learning, you have you can use NumPy, you can use even Torch or TensorFlow itself to split. If you have already loaded your data in arrays, in lists, you can use train test splitting scikit-learn to say what size of random basically split you want to have. Final slide. As I mentioned, many of these things are project task specific. I'm happy to discuss in a second if you have questions that I can help with. But the way that you can find answers to your questions, many of these, it could either be in papers. I've tried to put a few names from every kind of area. For example, AAAI is somewhere that you can find general machine learning AI. Pretty much from all areas in machine learning and AI. CVPR, ICCV are more computer vision if you're doing computer vision. ACL, EMNLP are mostly for NLP, natural language processing. And MICAI is specifically more to medical imaging stuff. So you might find better ideas, better solution in those papers. Or if you're using deep learning, there are these two big kind of the two biggest. In academia, mostly we are dealing with PyTorch. If you go industry, you can see that people are more basically comfortable with TensorFlow because of the efficiencies that it might have over PyTorch. And for classical machine learning, scikit-learn is a very good library. You have pretty much all of the classical machine learning methods, a lot of good functionalities. And then I've tried to put some specific libraries. For example, if you're doing NLP, big models like GPT, BERT, all those kind of things, Hugging Face is a very good library. For dealing with tabular data, Pandas is a very good library that gives you a lot of good functionalities. And OpenCV if you're doing some simple geometric and computer vision tasks. Um, so I think that's all I had to present. Let me just get to this question. Will we get feedback on the pitch presentation? Of course you will. So if you're able to refund, yes, the aim is hopefully by the end of this week or weekend, we submit the feedback online on my uni so you can see what score you got and why. We try to put some comments on that. Should also splitting take place before or after data pre-processing? That's a good thing. So you split your data set first. Again, for example, if you're doing a standardization, as I mentioned, you don't want to calculate things on the whole data. For example, mean and variance should be calculated based on your training data at first. So in that sense, you need to split your data set first and then use the training set to if you're doing standardization, for example, to calculate mean and variance and standardize. But every data that goes into your model, whether in training or testing, should be pre-processed and standardized in the same way. It's just that if you want to learn something from your data, if you want to extract some, as I mentioned, for example, some statistics like mean, you cannot use the mean that you have extracted from test or the whole data set and then use it on test set. There shouldn't be this overlap. That's the important part. You don't want to learn from testing set because then there's a leakage of information if you can see that. So if you calculate the mean from the whole data set and then split, you have already kind of seen the test set at the time that you are calculating the mean. So that's a leakage of information you need to be aware of. Okay, I can stop sharing the screen and I will be here for the next couple of minutes. If there is any questions, happy to discuss. You can also unmute yourself if you feel like. If not, if you have any other commitments, feel free to leave. And I think that's it. For the people who want to stay to have a chat or question answering, I'll be here for the next 5-10 minutes. Thank you, everyone.
Hi, Mehdi. Hello, sir.
Hi there. Just I'm not sure if you asked this question. The slides today will be put on my uni. Sure. Right after the lecture, I will put them. So now is Prashant, were you talking? Yes, go on,
I'm
please.
saying. Actually, my project is plant disease classification on the basis of the patterns on the leaves. So I was hoping if image segmentation will help me to remove bias, or will that decrease the accuracy of my project? I'm very much skeptical about it.
Let me first, maybe it's better to stop recording here.